whole range of branch instructions just now. And also there's compare instructions. And so we're just going to go through this, and we'll give just a resume of a resume of what is available, and that's relevant to the next exercise that you'll be doing. Just to reiterate and give examples of what we have. Here we have known A, $0 and dollar means text. This makes any difference, like hex 0.5 or decimal 0.5 is the same. No problem there. Then another like 1.5, then you have to define whether that was 15 decimal or whether it was 1.5 hexadecimal. It's quite different. Like 1.5 hexadecimal is what? If you had $1.15 there, what would that be? What would that number represent in decimal?
21.
Yeah, 21. Okay, 1 by 16. It's 3 plus 5 is 21. So if you had 1.5 there with the dollar, it would mean that the decimal value is 21, not 15. If you want it to be 15, you have the dollar sign. Okay? Sometimes you may also see a H after the number. That's another way that you can define a decimal number. So you can have 0.5H or 1.5H after the number. Then here the hash sign here means immediate address. So that means that the value 5 will go to cordinator A. You have the hash and load the contents of address 5 into the cordinator. Next one down, load cordinator A 005. That loads cordinator A with the contents of location 5. It's very similar to this one here, except you've got 0, 0 here. This is known as extended addressing. This one here is direct addressing, and it assumes that the top order of the address is between zeros. This one actually explicitly showed that the top order of the address is zeros. Why do you have two similar type of operations? Just that this operation here, this instruction here, occupies 3 bytes. 1, 2, 3 is the instruction here. This one only occupies 2 bytes. Okay, so it will execute faster. Here we have loaded with a hash 21. What will that do there? Well, there's no dollar, so this is actually the value decimal 21, and that will load the decimal value into cordinator A. So that will load the value 15 hexadecimal into cordinator A. Here we have clear A. This one here is just an EDNE address. This operation is just operating on an accumulator. So this is clearing accumulator A, and so this will have, in this case here, it's just one opcode. There's no address field here, it's just an opcode. So you can see here, these are the instructions themselves, 9605, 8605. In each case, the first byte is always the opcode. And then the successive locations, if they are relevant, contain the address or the values that you're going to put into the accumulator or memory library may be. Okay, and this one here, you have load index register. This will load the index register 1C00. So this is we saw yesterday is how you load the index register with a base address and then use that to go through successive locations. So for instance here, we load index register with 1C00. In the instruction itself, we're loading increment A with index addressing. So this is the contents of X, which is 1C00, and to that is added 6. Now it doesn't actually add it to the index register, it does it sort of offline, it does it sort of internally. So it calculates what's X plus 6, whatever that result is, that's the address that will be used in the instruction. So you can see the instruction uses address 1C06. So that's 1C06, that's what will be accessed with, the address that will be accessed with this particular instruction. And this will load the value of 87 into curator A. Now we'll have some branch instructions here. So we saw that you have a label. You always branch to a certain location. You have to have a label associated with a branch. So your branch we saw last year, you branch backwards to a certain position in the program. So you can branch backwards or you can branch forwards. If you branch backwards, then you have in the instruction you have a negative number, which indicates the number of bytes back that the program counter has to go to a particular instruction you want executed. So that's why we have choose complement. So here we have B and E branch dot equal branch to a label if the Z bit is equal to 0. Remember the Z bit, that's the bit in the condition code register. And all the branch instructions, apart from this one here, they check the condition code register for a specific bit. So this is checking to see if the Z bit in the condition code register is set to a 0. This will be set to a 0 if whatever was the instruction preceding this, immediately preceding this, had a 0 result. So we saw that you had decrement B. We saw that in the program yesterday or the day before. The decrement B, then you had B and E. So that was checking to see if the result of decrementing cumulative B was 0. If it was 0, then the Z bit will be set to 1, and this branch will not take place. Otherwise, it will take place. BEQ is a branch to a label, so this doesn't check anything. This is branch of equal to branch to a label. So if it's 0, this is if Z is set to 1, then you branch to the label. So that's the opposite to that instruction there. And then finally you have branch to go. This is a non-conditional branch. This just simply says go to wherever go is. Go is the label, and branch is an unconditional branch. So you have that if you want to sort of branch regardless of any condition, you just simply branch. And in both cases, both in this case and this case, in this case, you have relative regression. What that means is you have a number here, XX is a number, which will be added to the program counter if the branch is to take effect. So if the branch is backwards and you have to go back 22, say 23 locations backwards, then the XX will be minus 23. If the branch is to go forwards and the label is sort of 15 bytes forward, then XX will be 15. So you can see how it operates. The value at XX is actually program counter, depending on the branch takes place going on. So that's a quick overview. It gives you examples of all the varieties of instruction types and the way they operate. So you can see in every case here, as before, the first byte here, 26, 27, 0, always is the opcode. So the opcode, as we said, informs the computer what is the operation. 20 means the computer knows it's a branch operation. 27, it knows then it's to perform a BEQ operation. So the opcode always informs the CPU what the operation is. It also informs the computer about the length of the instruction. So the program will be incremented by the appropriate length. And also it informs the processor about the type of addressing mode. And you can see that in this one here. So here you have load accumulator A. Both of these are loading accumulator A. This one is loading it with the value, with the contents of 5. So it's 9.6. This one is this load is actually loading the accumulator with the value 5. So it's an 8.6. So you can see the opcode informs the processor what type of addressing mode is used, whether it's in this case direct or immediate. So that's all contained in the opcode, and the opcode is designed to do that. So that's how it happens. The design is designed the processor when you ensure that the opcode is sufficient to inform the processor what to do. And then another one that we have here is, so yeah, another one that you might see is jump. It's rather like a branch, but in this case it's extended addressing. So what you have here is instead of having relative addressing, you just simply jump, and you have a 16-bit there. because that is the address where you want to jump to in the program. So different opcodes, certainly, and this is, say, in this case, 2DF0, that's where you want the program to go to. So the label here is put in there. So it's another variation of a branch, except you're not checking. In this case, you're just jumping. You say go to a branch, so jumping to a location. So you're not checking a condition. You're not saying jump to equal to 0 or jump to greater than 0, but just jumping. It's like a branch. It's very similar to a branch, except the branch is using just one byte for the address, so you can jump to any address from 00 to FF. In the jump instruction, you have a wider range of addresses to jump to or branch to. Next one then are compare instructions, which are used quite extensively. You compare the contents of accumulator A or accumulator B with a value. So here we have, let's see, for instance, this accumulator B, does it have the value 2C? We saw before, you can just simply do a B and E, so branch range to 0, and check. It assumes you're assuming that you're checking to see if the value is 0. In this case here, we don't want to check the value is 0, we want to check if the contents of B happens to see some value 2C. So this instruction, when it's executed, it will take this value here, you can see hash $2C, so this is the immediate value. It will compare the contents of B with 2C. And the way it does it is that it doesn't actually affect any value, but what it does, it subtracts from B the value 2C. And if that result is 0, then it means the contents of B are the same as 2C. And in that case then, Z is set to 1. So this compare instruction can be used with a branch instruction. You have a B and E after this here, then a B and E immediately after this here. That branch would take place if the results were not comparable. They didn't compare successfully. If you have B and Q after the compare, it will branch if B contains the value 2C. Now it doesn't actually do the subtraction. It doesn't subtract this value from contents of B. But what it does, in another part of the computer, it performs that subtraction just to see if the result is 0. If the result is 0, it means they are the same. So that's how the Z gets set in that particular case. In this case here, it's very similar, except you're loading or comparing B with the contents of 2F1B. So you're comparing B to see if it has a value 2F1B. What else have we? Oh, we have logic instructions. So you can actually check. For individual bits. If you want to know if a particular bit in a byte is set to a value or not. So what happens here? We have an AND operation, and here we have an AND operation operating on A. And here we have the binary. The percent sign there indicates that we're dealing with the binary value here. We could put, instead of put a dot there, in which case we'd have to write in hexadecimal, so that's the way 2F or 2D or something like that. But this indicates that this is a binary value. So what is happening here? We're going to AND A with this value here and see what the result is. So assume A has the value 0, 1, 1, 0, 0, or 1, 1, 1 here. So that's the value in A here. Here's the value that we're ANDing it with. So that's it there. So ANDing A with this value here is performed here. So this is the value that happens to be in A. Here's the value that you're ANDing the bits with in A. And so you have 0 and 0 is 0, 1 and 1 is 1, etc., etc. So that's what the AND operation will do. This is the AND bits, yeah?
The furthest to the right entry on the first column, why is that a 1?
This here?
Other one.
Sorry?
The first column. The one on the left.
Sorry,
yes.
1 and 0 is an AND operation, gives you 0.
On the far right of that.
Oh, over here?
I'll come up there.
This one. Oh, sorry, that should be 0 there. Yeah, all right. Sorry, yeah, not spotted. Put that in this one. Do a mistake, not spotted. I didn't make a mistake. No, that should be one there. It's got one. That should be a 0 there. Yeah, that should be a 0 there. Yeah. So you can see just do the AND operation with each row of each column of bits. Okay. So why would you want to do that? How you might want to do that is say you want to check if a number is odd or even. Okay. If a number is odd or even, how would you know that in binary? So say you have a number at location. Okay, this is imagine. So you have a number, say at location 100. Okay. So at location 100, you have the number, let's just keep it very simple, the number 5. Okay. And you want to check, you don't know, I'm sure it's number 5, but say you want to check if the value at 100 is odd or even. What you can do is you can do something like the following, say load accumulator A with the contents of this here. So we have 0, 1, 0, 0. Okay, so you're going to load accumulator A with the contents of this. And then what you're going to do is you do sort of AND A hash % sign. Okay, and so if you look at this, a number that's odd in binary, what's distinctive about an odd or even number in binary? Yeah. So the way it is that you've got you've got 8 bits, and if you have a 0 there and the rightmost bit, then that means it's even. Okay. It's an even number. And if you have 1 there, it means that it's an odd number. So something like 5 here, that's 0, 0, 0, 0, and then 0, 1, 0, 1. Okay? You can see that one there. That's what we're saying here. The rightmost bit here indicates whether the number is odd or even. So you want to check the rightmost bit to see if that's 1 or 0. Okay? So we're going to add whatever is in A. So what we have here, so at the end of that operation, what we have here is we have in accumulator A, we have 0, 0, 0, 0, 0, 1, 0, 1. Okay, that's what's in accumulator A after we execute that instruction there. Now we want to check this bit here. So we can do that by using an AND operation, or equally we could do an OR operation. There's 2 ways in which you can do it, an AND or an OR operation. An OR operation is just going to do an OR operation, an AND operation is going to do an AND operation. Okay? So what we can do is, we'll keep with an AND anyway. So what we can do, if we were to take the value 1, 1, 1, 1, 1, 1, 1, okay? If this is the value that we're going to AND with A. So we're going to AND A with 1, 1, 1, 1, 1, 1, 1, 1. So we're going to AND it. What we should do, maybe an OR operation in this case. And what we would do, it's easier to show with an OR operation. So what we're going to do, we're going to OR A with this value here. So if it's just see if I should visual and or not. Okay. So say we OR this. Okay. We're going to OR this value with A, we're going to OR it with this here. If this is well, in this case here, what's the result? We're going to the general. So we've got 5 here, and we OR it with this here. So what's the result? Anywhere where there's a 1, it means that the result itself is going to be a 1 here. It's an OR operation. So what we're doing here, by putting an OR operation with 1s here, we're really ignoring the values here, because we know the result is going to be 1 regardless. So anywhere here, you're going to get 1s. The only place where it's questionable what we're going to get is this bit here. If that's a 1, and that's a 0, then we get, so if that's 1 and that's a 0, we get a 1 there. And that means that we have an odd number. If that was a 0 there, we have a 0 and a 0, and we get a 0 there, so that would be an even number. So you can see, we can actually mask out the parts of the bits that we don't want, we're not interested in, by an OR operation. We put 1s in here. The bits that we're interested in, this bit here, for instance, we put a 0 in the OR position. And the result of there means that if that is a 1 there, if it's a 1 here, if it's a 0 here, the result is 0. So what we can see here is that you can check for the result, or check to see if it has an even or odd number, by seeing if the result is equal to FF, okay, or not FF. Okay. So we have here no differentiated value, or it with this here, and then you can do something like compare a dollar FF, and then you have branch is not equal to 0. We only branch is not equal to 0. To it's not equal to 0, then you go to some part of the program where it's an even number. Is that right? So you see, if it's not equal to 0, it means that it's not equal to FF. It means that it's actually even. So you can see how that's how you check to see if a bit is set. We were interested in the bit that is here. Equally, you could check other bits that are inside the coordinator. So these are bit operations. All computers access a byte. That's the minimum that you can access in any computer system is a byte. But then you can check the value within a byte by using this type of logic masking, comparing. So that's how you can look at values to see maybe even different values internal to a byte. You have to pull the whole byte in and then use some masking like this here to see what the result is and determine. Yeah.
So for a byte, if you check the leftmost digit, that tells you if it's positive or negative. And
the rightmost bit.
The rightmost bit tells you the sign.
Yeah. And
then the leftmost bit tells you the...
No, well, if you wanted to check, if it's two complements, if you wanted to check, you could use that. You could actually check to see if the leftmost bit was a 1 or a 0.
Oh, so you'd have to do a separate check.
Yeah. Well, you
can't just like look at it.
Yeah. If you wanted to check, if this was a two complement number and it was positive or negative, what you could do, you want to check that bit because that's the bit in the two complement number that indicates whether it's positive or negative. You know, a 0 is an even, sorry, it's a positive number. It's a 1 is a negative number. So the way you can check that, if you had a value there and you want to check if it's a two complement that's positive or negative, then it wouldn't be, this one here would be 1 there. You're not interested in that there. You're just interested in this one here. So you put a 0 in that position and do an OR operation. And if that was a 0, this you have a 0 there, so you have a value which is not FF. If it is FF, it means that bit is a 1, it means that it is a negative number. So you can see how you can check different bits in the word. Now, you can check them at the end, or you can check bits in between.
Oh, you can?
Yeah.
Oh, okay.
Because it all depends what way you hand the operation. So if you were to, say, so if you had 1 here and 1 there, and you had 0 there, then you'd be checking to see what's the values there. You want to check if those values are 1, 1, you could put in 0, 0 here. And if they are 1, 1, the result would be FF. And if it's not FF, then they're not 1, 1 there. So you can check bits in between. Okay?
Yeah.
Yeah. So you can see how it's handy. We did the OR, you can do the AND, so there's the AND and OR operations, multiple operations that you can do. Okay, so that's that. Unless there's an OR operations, I'm just going through that. And then you have a NOT operation. A NOT operation means you get the value, and this simply not to convert it from it's what changes 1 to 0 to 0 to 1. So if that's the value in A, and you have to or neg A or not A, sometimes the same thing. I think it's not A or neg A, I can't remember very shape. But what that will do is just simply negate the 1s and the 0s complementary. So that's the basic operation. Ones that you use a lot, we load and store, get values in and out. So loads and stores are always quite prolific in any program. You're also going to have compare instructions, and then you're going to have branch instructions, and then you have varieties of those. But they constitute about 7% of all the instructions that you encounter, when you're writing programs at this sort of level. And the ones I've gone through really was everything that you need to know for the exercises that you're going to do. There's about 100 instructions in the 6800, but we're not going to go through all of them. We're just going to go through the ones that actually relevant to the exercises. Okay, so a lot of stuff there. And I'll just say, going back to just where we were before, just that you've got some.
Bless you.
Any questions on that? Is that okay? Yeah. No questions? No one went down last night to the Halloween parade on Pond Street. Apparently there was a fake. I was actually passing Pond Street on the bus about 8 o'clock, and there was literally thousands of people standing at the side of the road. And I couldn't understand why were so many people standing, along Pond Street. And apparently on social media there had been some fake information that there was a grand Halloween parade taking place down Pond Street. So everyone's standing there like nothing happened. But everyone's dressed up in costume, so I guess they were the carnival. But anyway, I just thought it was
People just put out like